Yeah, Vinay, go ahead.
Okay, so this problem, what it asks for is, so given the head of a linked list, return the node where the cycle begins. If there's no cycle, return null. So in this case, in the diagram we see, the cycle is starting at 2, and then it keeps going forever. So we return, the cycle would start at, like for example, node 2. Then what they say is, there is a cycle in a linked list if there is some node in the list that can be reached again by continuously following the next pointer, right? So you just follow the next pointer, and then if it goes back to the already visited node, then we know that there's a cycle. And then they give you some idea of internal implementation. So they say that internally, position is used to denote the index of the node that tail's next pointer is connected to 0 minus indexed. It is -1 if there is no cycle. And the position is not passed in as a parameter, right? So the position is basically 0 minus indexed index. For whatever reason they mentioned it, but they don't give us an input like position 1 or 2. They just give us a linked list. So just going by the diagrams, you have a linked list. 2 is 4 minus 4, which is the last node. The tail is connected to 2, so therefore there's a cycle. And then 2 is connected to 1, so there's a cycle. And here it's not connected to anything, so there's no cycle. That's the output they expect. And the number of nodes in the list is in the range of 0, 10 power 4. You can have 10 power 4 nodes, and the values can be negative 10 power 5 to positive 10 power 5. And position can start from -1 or a valid index if it's present in the linked list. And the follow-up, they just ask if you can maintain a constant memory instead of taking up more memory. That's the idea. Okay, I'll give you 10 minutes and we can talk about it. Okay. All right. Any ideas on how we would solve this problem, considering a brute force to start with? Okay. So the brute force, at least the one that I solved initially, was I would take a data structure to store these elements while I'm traversing, and at some point, the next node of the tail would point to the node that I already store in the data structure. So therefore, collection, for example, and then at each step, I would say if the collection contains the node, then return the node that is already contained in the collection. So therefore, the answer returned here would be 2. So basically, the time complexity for that would be order of n, because we would have visited all the nodes in the linked list by the time, and space complexity would also be order of n, because we're storing the nodes as we go. So therefore, the space grows according to the linked list. That's a brute force way I attempted initially before I realized there's a better approach. Any questions on the brute force approach? Okay. All right. Now, the more efficient approach, which would considering the constraint that we have, which is order of 1 complexity as far as the memory goes, is to employ the tortoise and hare algorithm. Basically, you would try and find if there is a cycle in the linked list by using that approach. One of the pointers, the tortoise pointer, will move slowly around the linked list, and then the hare would move faster. And then if they meet at some point before the linked list ends, we know that there's a cycle. And if the linked list, the hare pointer hits to a null, then we know that there's no cycle in the linked list. So there's no point in processing the algorithm forward to determine the entry point. So we just return at that point where we hit the null at the end of the linked list. Now, once we have determined that there's a cycle in the linked list, we would then move to a second step where we would still employ the tortoise and hare algorithm, but at this time, we would move the tortoise and hare pointer by 1 node each time. The tortoise will start at the start of the linked list, and the hare would start at the meeting point that we found earlier. And we just iterate the links 1 by 1. And when they meet at some point, we know that that's the entry point of the cycle. Any questions on what was explained so far? At least on the second approach.
So let's say if an example 1, if they're meeting at point 2, right? So
yeah.
So and
we could actually, let me draw something better than this one, so it'll be easier.
Yeah, I think first half was clear. I was just thinking about the case where
yeah,
it's pointing to, if -4 is pointing to 0, right?
Right.
So, I mean, I think in that case, the meeting point will be different, right? I mean, where they're the node at which we detect the cycle will be different, and then
Right.
yeah, okay, I think it might make sense. Yeah.
Yeah, so 3, 2, 0. Let's say the entry point. Oh, 2 has to be the entry point, right? We could do some approximation. So 6, 8, 9, 10. Yeah. Right. So when we are cycling through the first time, right? Let's say the tortoise is navigating a distance d, then the hare should go twice this distance, 2 times d. So the hare would do distance till this point, and then it would go here, right? Let's say the hare is here, right? Now, the idea is from this point, let's say the tortoise moved the remaining nodes. So let's call the total count of the nodes as C, for example. So if the tortoise would move C minus H nodes from this point. Now, similarly, we should factor in the hare should move twice C minus H from the point where it stopped, correct? So that would in turn become so basically this is how the phase one works. So the distance traveled by the tortoise eventually equates to the distance traveled by hare when there is a cycle. That's what they're trying to explain in the phase one.
Yeah, I mean, that sounds okay. I mean, if you, I was just thinking if we can take example one and do a dry run on the example one, just make sure like it connects to at second index, right? Like instead of that, if we connect at at 2, which is 0.
Which is 0, okay.
Yeah, if we have, yeah, exactly. So if we have a slow and fast pointer, I feel they still are going to meet at the last element, which is the index 3, right?
Index 3.
Yeah. So because the hare moves twice, so it will move to 0 in the first iteration, right? And the tortoise will be at 2, second iteration.
So let's see, tortoise and hare, they both start at same point.
Right.
And then tortoise moves here, and then hare should be here. Then tortoise moves here.
Yeah.
Hare should be next. Yeah. So they met at the same point. Let's do that again.
Yeah.
All right, clear all drawings, and how do I enter it again? All right. So 4 is connected to 0. Okay. So now this guy's our tortoise and this is hare. Now when we loop, tortoise will come here and hare will be here, correct?
Yep.
Now tortoise will come here and then hare should be here. Why? Because hare would move hare dot next dot next.
Yeah, right.
Yeah, eventually they'll meet. I mean, if we simulate, it'll be obvious, but I was trying to dig the actual reason why it's even working.
Yeah.
Yeah.
Yeah, I think it, yeah, because now if the head moves equal distance at the slow pointer or the tortoise, definitely they're going to meet at 0, which is the right answer, right?
Correct.
But in the original example, they will meet at -4, and then for part 2, the head moves 1 step, which is meeting at 2, and then the tortoise also moved 1 step, so they both meet at 2,
Correct.
right?
So let's say they met at 4. Here is here.
Mm-hmm.
Is a meeting point. Now, your tortoise will come back to this point. Now, tortoise will move 1 step. Hare will move another step. Only 1 step. It won't be moving 2 steps anymore. So they met. Then therefore we know, or at least if you just go by the algorithm, if they both indicate the same node, then we return the result as the same node. But then we can have questions from the interviewer, like, why do you think you have to reduce the speed of the hare? We thought like tortoise will move 1 step, hare will move 2 steps. And why did you take the tortoise back to the head? So those kind of questions is what I'm trying to answer.
You mean hare back to the tortoise speed, right?
Yeah, that's so 2 steps will happen. So first phase is basically finding a meeting point and then saying that, okay, we found the link, right? Cycle.
Mhm.
And then we record the meeting point, which let's call it H. But then the second phase is we would slow down the speed of hare to 1 node at a time. But on top of it, we move the tortoise back to the head. Right? So the tortoise won't continue from its own position. It has to go back to the head. Now, tortoise will keep going 1 step, hare will go 1 step, and then they meet at certain node. And if we find the node to be similar, that's when we return that node. And apparently that node will always be the entry point.
Yeah, I think interviewer might ask, why do you
Yep.
change here to the first node for, and why do you reduce the speed to half, right?
Exactly.
So he might ask, oh, I mean, I don't know how to convince for that part. Maybe if you know, you can let us know. But I usually go ahead with one more pointer, like let's say tortoise is equal to initially, right? Tortoise is equal to hare is equal to head. So after the first part is done, I don't disturb the hare. Okay, I just move the head and the tortoise since they with 1 step at a time. But again, it will be good to understand why. I mean, from your understanding, we move back here
Right.
to start and reduce the speed both. Then
Yeah. So initially, I was of the same opinion. So let's say our meeting point is here, and let's say the tortoise is somewhere here. Then I just reduced the speed of the hare by 1 node just because I wasn't completely sure what's going on. But this does not guarantee that they'll meet at the entry point. They can meet anywhere in the cycle, right? And I was checking my answers, and it did happen that they were returning a node that is not the entry point. So
sorry, what was the last sentence you said? I just missed it.
right. So what I did was I found the meeting point, and then let's say my tortoise is already in the cycle. It's not in the head anymore. Let's call it tortoise was here, and then sorry, my tortoise is here. So we found the meeting point to be this, right? So then I thought like, okay, let me, right now, both of these are in a cycle. They can't go back, right? Now, I was just incrementing initially the hare by 2 nodes and tortoise by 1 node and returning a common meeting point. But apparently it doesn't guarantee that the entry point will be returned. It can be any node where they meet, right?
Right. Yeah, that's right.
Yeah, so
That's true. And
there
also,
seems to be a explanation as to why we have to go back to head and why we have to reduce the speed of the tortoise. Sorry, hare. I will try, but unless somebody knows this 100%, maybe I might have some questions too. So what I learned is, let's see.
yeah, I think we can explain what you did before, with the help of the formula, right? If you divide that with some distance, right? Like x plus y, whatever formula you describe, that we can help.
Correct.
And one more good thing is like hare and tortoise thing. Hare can move with any speed. I mean, just a funny thing to notice. It can even move with 2x speed or even with 3x, 4x, 5x, whatever, how fast it want to move, just keep in mind. But if ever they meet, hare and tortoise, I call it slow and fast pointers, but if ever they meet, then it just simply donates that there is a cycle. That's it. It could be, so depending on what is the speed, it could be 2x, 3x, they can meet at any point. And once we detect it's the same thing, then one thing is confirmed, that there is a cycle. And as you mentioned, it may or may not be the entry point. So that goes with the logic and the pictorial way which you have described before. I think that's what even I think, unless you have anything or someone has any better explanation. Because even if you see the visualization, you can see like now we need to move from head equal distance from the meeting point, to get that point. And you can take multiple examples to illustrate. Like we just changed the meeting point from node 2 to node 0, right, in example 1. And again, it was like initially it was 1 step, and when we modified the example, it took 2 steps, right? So that can come up with a generic way of establishing that formula which you were trying to show us, I think.
Yeah. So like you said, if you just do a circling around with fast and slow pointer, we just know like there's a cycle. But yeah, this is more important and more trickier, I would say. It's not very intuitive, but so what they say is like, let's say this is a distance x, and let's call this as a meeting point, and this is y, and rest of the distances, let's call it z. So if fast and slow pointer start, and then they're circling around the link, the cycle. So by the time the slow pointer covers the meeting point distance, it would be x plus y nodes, right? Now, since fast pointer moves much faster than slow, it would have covered this point already. And then when it comes back to this, that's when it meets the slow pointer, right? So then our equation would then be x plus z plus y, something like that. Oh, it would have covered a cycle like that, and then that's what I think I read. And eventually it has to be the rest of the distance, because it already circled once, and then it has to travel another y distance to meet the slow guy. So therefore it's plus y is x plus y plus 2z. Oh, I'm sorry, 2y plus z. So based on this fact, they said if let's say this distance is covered twice, you have 2x plus 2 y now, which would then give x plus 2y plus z. That's because let's consider this as the fast pointer distance. It should cover twice the distance as the slow pointer now. And therefore, if you reorganize, eventually you'll end up with something like x would be z, because you cancel these out and you move this around. So basically what they mean is like, if your fast pointer ended up here, which is a meeting point, and then you pull your slow pointer back to x, by the time it comes to this point, from the fast pointer, if you keep going one node from here, the z distance will make sure that they hit the entry point. That's the idea. Yeah, I guess it goes a little overhead, but if you guys find some proof around online, it's pretty much boils down to this. Any questions or oh yeah, I forgot to show the code. Okay, I mean, the solution is simple, given we understand the actual mathematics behind it. So basically, you start your slow and fast at the same point, and then you have a meeting point where you keep, you know, brushing the hair, and the tortoise will go one node at a time, and at some point the fast is slow, then we found our meeting point. And if the meeting point is null, before the fast hits null, then we know that there's no cycle, therefore we return null. Then we bring the slow pointer back to head, and the fast pointer still stays at the meeting point. Now, going by the second phase that I just explained, we just move these nodes one by one, and at some point you'll see that slow and fast are similar. Then you return the fast as the entry point. Okay. I think Sagar might drop off. Yeah. So I'm done with this algorithm. If anyone else has